Okay, in this series of videos, we're going to be talking about channel coding. Channel coding is where you insert some redundancy back into the source stream of bits so that you can use that to combat noise. Remember, with source coding, the idea is to extract all the redundant information out of the signal and send only what's absolutely necessary. Okay, so we gave an overview of how you would do that with a discrete alphabet. We use that Huffman code, and we can see where if you had redundancies in the code, you could extract that to get the average code word length down. All right, this is actually more interesting when you take a look at things like audio and video. So it turns out those things that use the statistics of what speech signals look like to crunch down the number of samples that you need. We call that data compression. All right, so if we can reduce that down to just the bare minimum that you need to produce good quality speech, then you can more efficiently transmit things, using a finite bandwidth and certain signal to noise ratios as predicted by the channel capacity theorem. Okay, so source coding is one thing. You strip the redundancy out. Channel coding, you put the redundancy back in there in a controlled way so that you can reliably communicate over a noisy channel. Okay, so the way these things go back in is with parity bits. All right, so our goal here is to add parity bits to our data stream. We want to do that in an efficient way. We're going to start out with an inefficient way. We're going to start out with just repeating the message that we want to send. Okay, so we want to do it in an efficient way, and we want to reduce the channel errors that are caused by noise. All right, so here's the roadmap. The first thing I'm going to do is I'm going to talk about the sort of the easy case, the intuitive thing, what you would try as a first step. And we're simply just going to use what we call a repetition code. These work, they will reduce the probability of error for a communication system, but they're not very efficient because you just keep adding bits and the overall data rate takes a hit. All right, so what we'd like to do, well, before I leave repetition codes, I also want you to be aware that there's a trade-off in a code between detecting errors with a code and actually correcting errors with a code. All right, so that's an interesting aspect of coding theory that I want you to also be aware of. Okay, so we're going to start out with repetition codes and talk about those things, and then we're going to wrap up the first video, and from there we're going to talk about a more complicated scheme. It's not super complicated. These are called linear block codes, and these have been used quite extensively in communication systems, although modern cell phone communication systems and things use much more complicated codes than just block codes. All right, so what I wanted to do is show you a simple example. It's like peeling back the layer of the onion. Can we do better than a repetition code? And yes, we can. We're going to use a linear block code. And so we're going to see that there's a concept called the distance of a code, and the distance helps us combat errors. If we have a larger distance within a code, there's less probability of error. Okay? So we're going to have an equivalent distance with a smaller block size, which means we can transmit this code more efficiently. All right, so maybe for now this doesn't make sense to you, but hang on, hopefully it will. So our goal was to beat, our goal here for this second video is to beat the repetition code and have it be more efficient, and we'll be able to do that. But you'll see it comes at a cost. It's slightly more complex. All right, it's not super hard to do a linear block code, but it does add some processing time and some complexity. All right, in general, that's the trade-off that you also see that comes out of the Shannon channel capacity bound. There's a trade-off between how much data you can send through a system and how complex the decoding system starts to be. And sometimes that complexity shows up in the form of delay. We just have to process the signal for a long time to undo the source coding, to undo the channel coding, and to get efficient communications. You've probably seen this happen with your HD TV, high definition TV, the decoder. It has to decode that source coding step, and there's some channel coding steps that happen in there as well. And all that takes a little bit of processing time. So there's several seconds of delay that you see coming through a system like that. Okay, so that's the roadmap. Let's get started with repetition codes. Okay, so let's say we were trying to send just zeros and ones. All right, so we send a 0, and there's a certain probability of error that might occur. All right, sometimes people draw this out as the binary symmetric channel. Okay, we send a 1. If it goes straight through, there's no error, but there's some chance of an error, okay, given by this diagram. So let's say, it's a really bad system, and you have a point, let's say 4 chance of, let's make it bigger than half. A 0.6 chance of sending 0, you receive a 0. 0.6 chance of sending a 1, you get a 1. So that would leave these other paths at 0.4 and 0.4. Okay? So if you broke this down into conditional probabilities, the probability of the output equals 0, given the input is equal to 0, is 0.6. All right, so those give you the conditional probabilities. All right, let's say that we wanted to transmit a 0 through this channel. Okay, what is the probability of an error? Okay, well, you can just get the overall probability of an error. Let's say that in advance we know that the probability of a 0 being sent is the same as the probability of a 1. They're equally likely. Okay, so on error, the error rate would be the probability of sending a 1 times the probability of getting a 0, the output equals 0, given that we sent a 1, plus the probability of sending a 0 times the probability that the output is equal to 1, given we sent a 0. Okay, so you can plug those in. 0.5, this conditional probability is 0.4, plus 0.5 times the conditional probability of 0.4. So you get a 0.4 probability of an error. Okay, so we could combat that by, let's use the channel twice. Okay, so we're going to send a 0, 0 to represent a 0, or a 1, 1 to represent a 1. Okay, so you can go through the calculations. If you send 2 zeros in a row or 2 1s in a row, and those are your 2 choices, okay, then skip all the math, but basically the probability of error goes down a little bit because it's 0.4 squared if you use an independent assumption on using the channel. Okay, so that's good. 0.4 squared is less than 0.4, so we've improved the probability of error. So if we just keep adding, if we keep repeating that bit, this would be like a repetition code, and you would see if you used it 4 times, the probability of error would be 0.4 to the 4th. And so obviously as you drive this down, 0.4 to the n, there is some n big enough to where you're driving the probability of error down to something small enough. Okay, so that's the basic idea behind using a repetition code, is you keep repeating a digit, sending it. You do that enough times, and as long as you can get this number to be small enough, then you'll be able to reliably communicate over the channel. All right, so let's think about that. Let's say we had a repetition code of 0, 0, 0 and 1, 1, 1. Okay, so people come up with an idea, and they call the idea here being the distance of the code. All right. So if you wanted to look at the distance of the code, you see how many bit positions the code words differ by. All right. So in this case, I think it's obvious that the distance of the code, I'm going to call it dmin because you could have more than 2 code words, but with just 2 code words, this is pretty easy to calculate. Dmin in this case is 3. All right. This code word and this code word, they differ from each other by 3-bit positions. Okay. From there, you can come up with a relationship 2t plus s being less than dmin. Okay, so basically you find integer values of t and s that work, and that gives you an idea about the error detection versus correction capability of the code. All right, so let's give an example. If I make t equal 0, okay, then s can be as large as 2. All right, for this particular code, because if I plug in s equal 2, 2 is strictly less than 3, this works. Okay, so it turns out that this repetition code can detect 2 or fewer errors. All right, so how would that work? Well, let's say we transmitted 0, 0, 0. And we got 2 errors, okay? So that would mean we'd have a 1, 0, 1, for example. Just randomly choose 2 bits to flip, 2 out of 3, okay? Since this is not a code word exactly, you could say, oh, because it's not 1, 1, 1 or 0, 0, 0, I'm going to say, hey, there's an error, all right? Okay, so in this case, any 2-bit error could be detected. All right, so there's that example. Now let's choose t equal 1. And if you have t equal 1, that implies s is equal to, well, 2 times 1 plus s has to be strictly less than 3. S needs to be 0 for this to work. Okay, so the t value tells me, I have t equal 1, I can correct a single bit error, but that's it. I can't, any kind of detection of errors, that's not going to happen with this particular code. We'll do a different example in a second where you can have both. All right, so let's think about that. This is a different decoding rule. You have to choose in advance whether you're going to detect errors or correct errors or some combination thereof. All right, in this particular case, we can't do both because if we choose to correct a single bit error, we can't detect any other errors. Okay, so let's think about that. If I had 0, 0, 0 and I was sending it, okay, then if I received a 1, 0, 0, I could look at this and use a majority rule. Okay, majority rule would say I got 2 zeros and a 1. I'm going to decode this into a 0. Majority wins. Okay, 1, 1, 1. If I flipped a single bit, majority rule says this would decode to a 1. All right, so if you think about it, a bit error in any position can be corrected. Okay, as long as there's only 1 that occurs, it will correct that error. Okay, so why can't it detect errors that are bigger? It's going to correct all single bit errors. Can it detect 2-bit errors like it did in the previous case? Well, if I had 2-bit errors, all right, flip any 2 bits, all right, I would then use the majority decoding, assuming that only 1 bit got flipped, and I would decode that as a 1, which is clearly incorrect, right? So I have no way of detecting it because the code word that shows up would be decoded under the majority rule, all right? So I can't do any kind of detection of errors. I can only correct the single bit error with this choice of T and S. Okay, so let's do one more example with a longer code, all right, to show this trade-off. All right, so let's say we had 7 bits. Okay, so we're going to send 7 zeros to represent a 0 and 7 ones to represent a 1. Okay, the minimum distance of this code is 7 because the 2 code words differ by 7-bit positions. Okay, now we have options. All right, let's choose one. Okay, let's make t equal 0. If t is equal to 0, s is equal to 6. All right, so what that tells me is I can detect that there's an error. My iPad broke. Let's explore this idea of the difference between correcting an error from the code and simply detecting an error, and how a code has the capability of doing both, but up to certain limits. Okay, so in this example, we are going to do a repetition code. So if I want to send a 0, I send a 0 7 times. And if I want to send a 1, I send the 1 7 times. Okay, so the distance of this code, remember the distance is the minimum number of bits that differ between code words. Well, there's only 2 code words in this case, so there's a 7-bit difference between these 2 code words. All right, so now we have some options to look at whenever we are decoding this code in the presence of errors. Okay, so the inequality goes like this. It's 2t plus s has to be less than d min. All right, so let's consider the case where t equal 1. When we choose t equal 1, that means we can correct a single bit error. From there, if I choose t equal 1, the largest value of s that solves the inequality is s equal 4. All right, so s is equal to 4 in this case. So what that means is we can detect t plus s in this case is 5 or fewer bit errors. Okay, so correct a single bit error and detect 5 or fewer bit errors. So let's take a look at how that would work. Let's say we want to transmit a 0. And let's say we received a single bit error. Something like that. It can be in any position. Our decoding rule would be if you have either a 0, all zeros, or all zeros with the exception of a single 1, you would take that and you would map that into 0. Okay? The only way you can get an error like that is if there's a single bit error or fewer. I mean, if there's no errors, it's clear what you do. Okay? So contrast that to if you had 2 bits of error. Okay? So let's say I had 0, 1, 0, 0, 0, 0, 1, 2, 3, 7. Whoops, I forgot to put the error in. there's 2 errors in this case. Well, is there really a difference between this case and the case where there's 5 errors? Okay, so if I took all ones, 1, 2, 3, 4, 5, 6, 7, and I flip every bit here except these 2, don't I get the same code word? All right. So if I can't tell the difference between a code word, a received pattern that has a 2-bit error pattern and one that has a 5-bit error pattern. All right. So the best I can do in this case, since there's more than one positional difference between the code word that I'm deciding on and the one that was transmitted, I'm deciding in this case that I can only detect this. All right, so if I receive this, I would say, oh, there's an error in here, and I'd be able to detect 5 or fewer errors with this scheme. Okay, well, let's do one more to see if it makes sense to you. Okay, what if I put t equal 2? All right, if I have t equal 2, I have 2 times 2 plus s less than 7. So s, the biggest s can be, is 2. All right, so in this case, with this pair of t and s, I can correct all 2 bits and fewer errors. All right, if I know for sure that there's 2 bits or fewer, I will receive the correct code word. And I can detect t plus s 4 and fewer bit errors. Right, it's the same kind of thing. So if let's say I take 1, I'm going to transmit 1, and I have only 2 errors, so maybe I get some pattern that looks like this. Okay. My decoding rule would be if there's, there's 5 of the same, all right, because there's 5 or more of the same, I would decode this to what the same is, all right. So there's 5 ones in this case, I would decode this to a 1. And I know because there's only 2 bit errors here, that was correct. I'm assuming there was at most 2 bit errors, this would correctly decode to a 1. Okay. So if I had 4 errors, all right, here's the same code word. I'm going to transmit a 1. If I have 4 errors, 1, 2, 3, 4 errors, okay, I could only detect that, right? And the reason I can't detect 5 errors is if I went to the 5th, okay, well, keep in mind the decoding rule was I have to have 5 or more of the same digits. 1, 2, 3, 4 zeros and 3 ones. Since I don't have 5 or more, I'm just detecting. Okay, and you see why that would be the case. If I had 5 errors, this would look like 0, 0, 1, 0, 0, 1, 0. So now I have 5 errors. This would fit the decoding rule. 1, 2, 3, 4, 5. 5 of the same digits. The decoding rule would say that should be sent to a 0. Okay, so I can't simultaneously correct 2 bits and detect 5 errors. Okay. All right, so hopefully you see as I walk through that, I didn't say that in the most elegant way, but hopefully you can see what I mean. There's this trade-off between number of bits that you can correct and the number of bit errors that you can detect. Okay, with that being said, let's now move on to the case where we have linear block codes. Remember, the goal here is to show that we can get the same level of error correction or detection in a more efficient way where we don't have to have as long of a code.